Good morning, chemistry students. Here are your Chapter 7, Day 3 notes. Today, we're going to be starting on your outline at 7.2, mole mass and mole volume relationships. And we will finish up and stop just before the volume of a mole of gas. So again, remember that you should probably have your chemistry toolkit out. Okay, oops. You want to have your chemistry toolkit out because we're going to add to it. Today, right now, you should have one, or depends on which way you did it. You probably have 3 tools on your toolkit that you use for counting. Remember, again, we want to kind of focus on the fact that when we talk about measuring matter, there's 3 ways we can measure matter. We can count, and we talked about those conversion factors the other day. So those were 1 mole of molecular compound is Avogadro's number, 6.022 times 10 to the 23rd molecules. 1 mole of ionic compound is 6.022 times 10 to the 23rd formula units. And 1 mole of element is 6.022 times 10 to the 23rd atoms. Today, we're going to start to talk about using the mole for mass. And remember, our third way of measuring matter was volume, which we will talk about in the future. Okay? So, again, you're going to want to have a calculator handy. You're going to want to have your periodic table handy. You're going to want to have your chemistry toolkit handy. So, make sure you have those things ready as we get ready to start our notes today. So we are going to start by talking about the molar mass of a substance. And again, you were introduced to this the other day on the ChemQuest, okay? But today, now we're going to kind of take some specific notes about it. So, and we looked at this on the ChemQuest the other day. The atomic mass of an element which is the mass of a single atom is expressed in atomic mass units, which are abbreviated AMUs. So remember we looked at that the other day on the ChemQuest. We said that average atomic mass that's on the periodic table, if we take that number and we express it in AMUs, we're talking about the mass of one single atom of that element. Remember, we learned quite a while ago that atomic mass is a relative unit. Okay, it's measured relative to other substances based on the mass of carbon-12. So a long time ago, back in Chemistry 1A, back in Chapter 5, we talked about calculating the average atomic mass of those elements that are on the periodic table. Remember, we said it took into account all the different isotopes. And those units, the actual masses of elements is so tiny that the numbers weren't something that scientists would want to work with, and chemists in particular. So instead, they compared all the atoms to carbon-12. And they did that because, remember, 1 atomic mass unit equaled the mass of 1 neutron or 1 proton. Okay, so I'm just reminding you that those atomic masses are relative based on the mass of carbon-12. Remember that they are not whole numbers on the periodic table. because they are a weighted average mass of the isotopes of each element. Remember, isotopes were atoms that were the same element, which meant they had the same number of protons, but they had different numbers of neutrons, which meant they had different mass numbers. Okay? Now, on that ChemQuest, we did see that the atomic mass of an element expressed in grams is the mass of a mole of the element. So again, we did that on that ChemQuest. We said, now if we take that average atomic mass that's on our periodic table and we express it in grams instead of atomic mass units, right? Atomic mass units, I'm talking about one single atom. But when I take that same number and I express it in grams, now I'm talking about a mole of those atoms, which means I'm talking about 6.022 times 10 to the 23rd atoms of that element. And that is what gives us our definition for molar mass. Molar mass is defined as the mass of a mole of an element is its molar mass. The molar mass, and we can kind of say that this is going to be expressed in grams. So molar mass is the mass of a mole of an element, okay, expressed in grams, okay, and the molar mass of any element contains 1 mole, or that Avogadro's number, 6.022 times 10 to the 23rd atoms of that element. And again, you saw that on that ChemQuest the other day because you took the mass in grams from the periodic table and figure out how many atoms that was of that element, and every time you ended up with 6.02 times 10 to the 23rd. Another way to think about this is to think about the fact that the molar mass of any two elements must contain the same number of atoms. So what we're saying here is because the molar mass of an element is always 1 mole, and 1 mole is always 6.022 times 10 to the 23rd atoms, if I have the molar mass of hydrogen and the molar mass of oxygen, because by definition they contain Avogadro's number of atoms, they contain the same number of atoms. Again, another way to sort of define molar mass is to say it is the amount of substance that contains the same number of representative particles as the number of atoms in 12.0 grams of carbon-12. Right? So this number here, this is the molar mass of carbon-12. Okay, which means it would have 6.022 times 10 to the 23rd atoms, right? And molar mass, by definition, has 6.022 times 10 to the 23rd atoms. So that's another way to potentially define molar mass. So one of the things that people sometimes struggle with is this idea that if you take a look at your periodic table, okay, hydrogen is a really small atom. So it takes, or let's say lithium. Lithium, 6.941 grams of lithium is 6.022 times 10 to the 23rd atoms of lithium. For bismuth, Bi, 209 or 208.98 grams of bismuth is 6.022 times 10 to the 23rd atoms. So sometimes one of the concepts that my students have struggled with in the past is this idea that how can 6.022 times 10 to the 23rd atoms of bismuth have a mass of about 209 grams, while 6.022 times 10 to the 23rd atoms of lithium has a mass of about 7 grams. Okay? So, to kind of help you think about that, okay, we have sort of a real-world connection here. And this real-world connection relates to eggs. So, I want you to think for a moment about going to the grocery store and buying eggs, right? We pretty much always buy eggs by the dozen. So, you buy a dozen eggs. Now, even in the grocery store, sometimes you can find different size eggs, right? There are small eggs sometimes. There are medium-sized eggs. There are large eggs, and there are extra large eggs. Now, hold on just a second. My dog's at the door. Now, if you compare the mass of a small egg to the mass of an extra large egg, do you think they have the same mass? They don't, right? Because a small egg is a much smaller egg. It contains much less matter, and so it has much less mass than a large egg. Let's exaggerate this, okay? Let's imagine you're buying a dozen chicken eggs. Let's even say large ones or extra large ones at the grocery store, right? Let's say at the grocery store you could buy a dozen ostrich eggs. Ostrich eggs are much, much bigger than chicken eggs, right? A dozen ostrich eggs is going to have a very different mass than a dozen chicken eggs. But I'm still buying a dozen. It's still the same number. What's changed is the size of those eggs, and therefore the mass of those eggs. So the mass of a dozen ostrich eggs is a lot larger than the mass of a dozen chicken eggs. Okay? Same idea applies to atoms. The mass of 6.022 times 10 to the 23rd atoms of lithium, which is a relatively small atom, compared to the mass of 6.022 times 10 to the 23rd bismuth atoms, which is a relatively large atom, right? It's the same number of atoms both times, but the mass is going to be different because the relative sizes of the atoms are different. Just like the mass of a dozen chicken eggs is different than the mass of a dozen ostrich eggs. I'm still talking about a dozen eggs. I'm still talking about 12 of each. But because the size of the eggs is a lot different, the mass of a dozen is very, very different. Okay? So that's kind of the real world connection to help you think about how it is that 6.022 times 10 to the 23rd atoms of some element can have such different masses. So to kind of jot this down, right, you can buy small, medium, and large eggs. The size of the eggs doesn't affect how many eggs are in a dozen. Similarly, the size of the representative particle doesn't affect how many are in 1 mole. Okay, so just kind of keep that in mind, that we can have the mole of atoms of potassium be 39 grams and a mole of arsenic atoms be 75 grams. It's still 6.022 times 10 to the 23rd atoms in both instances. The difference is potassium atoms are about half the size of arsenic atoms. Okay? So that brings us to kind of our first problem. And we're going to look at, I want you to kind of figure out the molar mass of sulfur, carbon, and iron. And remember, molar mass is always going to be measured in grams per mole. So, how do we figure out the molar mass of sulfur? Again, we're going to take a look at our periodic table. And we're going to find sulfur. Here's sulfur. I should have used a different color. Here's sulfur, right? And here's our mass, 32.065, 0.059, something like that, right? So we'll say 32. So, okay, the mass of sulfur is 32 grams per mole, the molar mass of sulfur. That means that if I have 6.022 times 10 to the 23rd atoms of sulfur, which is equal to 1 mole of sulfur, I'm going to have 32 grams of sulfur. That's what this is saying. So, take a moment and figure out the molar mass of carbon and iron, right? You're going to go to your periodic table, find the average atomic mass, and express that average atomic mass in grams per mole. For carbon, it's 12.011 grams per mole. And for iron, it is 55.84 0.045 grams per mole. So, we have a new conversion factor again, right? We have another tool for our toolkit. Remember our 3 ways to measure matter. The count. You already have the 3 tools on your toolkit for counting, right? The 1 mole of element is 6.022 times 10 to the 23rd atoms of that element. 1 mole of molecular compound is 6.022 times 10 to the 23rd molecules of that compound. And 1 mole of ionic compound is 6.022 times 10 to the 23rd formula units of that compound. Okay, those were the count ones. Now we're adding the mass one. Now this mass one has a name. It's called molar mass. Okay, and it's some number of grams of our substance over 1 mole of the same substance. And again, remember the power of this is, and I wouldn't recommend you really write both of them on your toolkit, but I'm just reminding you again that depending upon where we need our units to be so that they will cancel out like algebraic letters, I can put my units wherever I need them to be. Now, where do we get this number of grams, right? That comes from our periodic table. So, again, this is a spot where I'd like you to really pause the video for a moment, find your chemistry toolkit. After you've written this in your outline, copy this conversion factor because now you should have 4 tools on your chemistry toolkit. So this is your mass tool. You have the 3 for count. Now you have the new one for mass. So we talked about the molar mass of an element. We also can do this for compounds. So to find the mass of a mole of compound, and it doesn't matter whether it's an ionic compound or a molecular compound, you must know the formula of the compound, which again is why it's so very important that you know, okay, how to write the formulas given the names for ionic and molecular compounds. So, for example, sulfur trioxide. Right? Remember, our first question has to be, is this compound ionic or molecular? Now, this compound is molecular because it's made of 2 nonmetals. Remember then to write the formula for a molecular compound, my prefixes become my subscripts. You don't have to have those prefixes memorized. They're on your helper sheet. There is no prefix on sulfur, so there's just one of it. And tri is 3, so it's SO3. Now we know that 1 SO3 molecule is equal to 1 sulfur atom plus 3 oxygen atoms, right? That's what our subscripts are telling us. So, how do I calculate the molar mass of this compound? Okay. I usually kind of write it like this. So I write, I have oxygen in this compound. I have 1 sulfur and I have 3 oxygens. Now I need to use my periodic table, and I'm going to go ahead and just use 1 decimal place, okay? We'll talk in a minute about how to decide how many decimal places to use, but for right now I'm just going to use 1. So I'm going to look at my periodic table for sulfur. And I'm going to find sulfur, and I'm looking at its average atomic mass. Okay, and I'm going to do the same thing for oxygen. So sulfur's average atomic mass on the periodic table, right, that big long decimal number, is 32.1 if I use 1 decimal place. For oxygen, I'm going to use 16.0. It's 15.999, which becomes 16.0. Okay? So now, 1 times 32.1 is still 32.1, right? 3 times 16 is 48.0. And now I'm going to add these together, which is 80.1. That's the molar mass of sulfur trioxide. 80.1 grams per mole. So notice how I did that, right? I added the mass of all the atoms in the compound. In this compound, there was 1 sulfur and 3 oxygen atoms. So I had to multiply the molar mass of sulfur by 1 and the molar mass of oxygen by 16. Okay, and so I got my molar mass of my sulfur trioxide. Now, one note about this. I'm really picky about you showing work, but you do not need to show work for calculating molar mass. Okay, now I'm not going to mark it wrong. If you choose to show that work, that's perfectly fine. Okay, and in our notes as we're doing these, I'm going to show work just in case there are some people who are still not quite sure where we get these numbers from. But know that on homework assignments and tests and quizzes, molar mass is about the only thing that you don't have to show me work for. Okay, so to kind of summarize what we just did in words, right, to calculate the molar mass of a compound, find the number of grams of each element in 1 mole of the compound. Then add the masses of the elements in the compound. Right, and that is what we did here, right? This is right here, right? This is the number of grams of the element sulfur in 1 mole of the compound. This is the number of grams of oxygen in 1 mole of the compound, and then I added them together to get my molar mass. Okay, so that was what we did. So, here's another problem I'd like you to do. I'd like you to calculate, and again, you don't necessarily have to show work, but calculate the molar mass of water, and glucose, which is C6H12O6. So again, if you need more time than I give you, pause the video and go ahead and do this. So again, I'm going to show my work just so that everybody understands where we get this from, right? Water is H2O. So I have hydrogen and I have oxygen. I have 2 hydrogens. I have 1 oxygen. I'm going to go ahead and use 1 decimal place again. So hydrogen is 1.0 and oxygen will be 16.0. Those numbers came from the periodic table. So this is still 16.0. This is going to be 2.0. Now I add them together and I get 18.0 grams per mole is the molar mass of water. For glucose, I have carbon, hydrogen, and oxygen in the compound. I have 6 carbons. I have 12 hydrogens. And I have 6 oxygens. Carbon's atomic mass is, okay, with 1 decimal place, 12.0. Hydrogen is still going to be the 1.0. And oxygen is still going to be the 16.0, right? Again, those numbers came from the periodic table. So, okay, 6 times 12 is 72. This is going to be 12.0. 6 times 16 is 96. Now I'm going to add these all together. And I get 180 grams per mole as the molar mass of glucose. Okay? Now, these both happen to be molecular compounds, but I would do exactly the same thing if I was dealing with an ionic compound. Okay? I still would figure out how many atoms of each there were, multiply it by its mass, and then add those masses together. So, we can use the molar mass of an element or a compound to convert between the mass of a substance and the moles of the substance. Okay, so again, this is a good time to have out your chemistry toolkit, right? And we have that new tool on there called molar mass. So here's our problem that we're going to look at. And we're going to actually look at 2 problems. And this is the last thing that you need to fit before the volume of a mole of gas. So this is sort of the end of our notes for today, are these 2 problems. So our first problem is, what is the mass in grams of 9.45 moles of aluminum oxide? So again, as I've mentioned before, I don't like story problems. So I'm going to take the problem and I'm going to kind of summarize it so I can look back at it easily and know what I'm doing. So this problem is asking me to take 9.45 moles, and I'm going to go ahead right now and write my formula for aluminum oxide, which you should be able to do, right? Aluminum oxide, it's a compound, so the question is it ionic or molecular? It's ionic because it's a metal and a nonmetal, so I'm going to do my symbols, my charges, crisscross, and make sure it's the lowest whole number ratio. So 9.45 moles of aluminum oxide is how many grams of aluminum oxide? So the question is, again, for those of you, you're new at this, right? I've been doing this a long time. But you're new at this, right? So the question is, do I have a tool on my toolkit that has moles and grams in it? Yes, I do, right? That tool is called molar mass. So I know I'm going to have to use that molar mass tool to solve this problem. I'm still going to start with my given. I always start with my given, which was 9.45 moles of aluminum oxide. Now, where do moles have to go? Where they're in the numerator. I need them to cross out. So moles of aluminum oxide has to go on the bottom. Now, my molar mass toolkit, one of the units is moles, the other unit is grams, so my other unit up here is going to be grams, and it's still the same substance. Now, moles have crossed out. I'm left with grams. Is that what I want? Yup. Now, numbers, right? On your chemistry toolkit, you should have 1 written in front of moles, right? Always in front of moles is 1. How do I get this number that goes in front of grams of aluminum oxide, right? That's where I'm going to use my periodic table. Again, I'm going to show you this work real quick, but this is not work you have to show, right? So aluminum, there's 2 aluminums. For oxygen, there's 3. Now, here's where I want to pay attention a little bit to significant figures. In terms of significant figures, right, this has 3 sig figs. I want to make sure then that my mass has 3 significant figures. So, to cover my butt, okay, I'm going to use 2 decimal places just to make sure. So, aluminum, 26.982, so 26.98. And oxygen, 15.999, which gives me 16.00. Right? I'm doing that same thing that I was doing. So, 2 times 26.98 is 53.96. 3 times 16 is 48. I add those 2 things together, and I get 101.96. So I'm putting in here 101.96. Okay, so that's where that number came from. Again, you can just leave it in your notes. I just am running out of space to do my problem here, so I want to give myself some space. So, okay, now I'm ready to do this on my calculator. I'm multiplying because both of my numbers are in the numerator. So on my calculator, I'm going to plug this in, right, as 9.45 times 101.96, and I'm going to hit my enter. Okay, and I get 963.522, but I have to do significant figures as well. So, again, our number our first number has 3 significant figures. It turns out we ended up with 5 significant figures here, so that's okay, because remember our answer is always limited by our number that has fewer significant figures. So our answer is going to have 3 significant figures. So I would say we'd say it's 964 grams of aluminum oxide. So remember I told you we were going to do 2 problems. So let's take a look at our second problem. Our second problem is how many moles of iron 3 oxide are contained in 92.2 grams of pure iron 3 oxide. Again, right? I need a chemical formula. You should be able to pause this video right now and write your formula for iron 3 oxide, right? First question, is it ionic or molecular? It's ionic. So I write my symbols. I write my charges. I crisscross. I make sure it's the lowest whole number ratio. So this problem is asking me to take 92.2 grams of Fe2O3, right, when you write your chemical formula, equals how many moles of Fe2O3, right? And that comes from iron is Fe, the 3 is telling me the charge on iron, oxide is O, it's in group 6A, so it gains 2 electrons, so it has a -2 charge, so it's Fe2O3, okay? So, again, the question is, do I have a tool that has grams and moles in it? I do, right? It's called molar mass, so I know I'm going to use molar mass as a conversion factor. So I'm ready to start my problem. I'm going to start with my given, my 92.2 grams of iron 3 oxide. Now, I know that this tool is going to be molar mass here, but where do I need my units to be? Right? I need, grams are in the numerator, so I need grams to be in the denominator so that they will cross out. And when I look at my chemistry toolkit, the other unit in molar mass, my molar mass conversion factor, is moles. Grams are going to cross out. I'm going to be left with moles, which is what I want. All right, numbers now, right? Easy number should be the number in front of moles in molar mass because it's always 1. Where do I get this number? Right? I use my periodic table. So again, I'll show you that work. Right? Iron there's 2 of. Oxygen there's 3 of. I want to make sure I use at least 3 significant figures when I'm calculating this molar mass. So iron's molar mass is 55.8. Oxygen is still 16.0. I'm going to add them together. Okay. So 55.8 times 2 is 111.6 plus the 3 times the 16, and I get 159.6 grams per mole. That's my molar mass of my iron 3 oxide. So again, the number in front of moles is 1, so 159.6 goes in front of grams. So this time, right, Because my mass is in my denominator, I'm going to divide by it. So putting this in my calculator, I'm going to do 92.2 divided by 159.6 and hit my enter. Now, again, if I want to take a look at significant figures, right? I have 3 significant figures here. This is kind of a definition, so that's unlimited, okay? This has 4 sig figs. When I'm multiplying and dividing, I'm limited by my number that has the fewest, which is my 3 sig figs. So when I do this on my calculator, okay, when I take my 92.2 and divide it by 159.6, I get a big long decimal number. But I need to write my answer with 3 significant figures. So you should get 0.578 moles of Fe2O3. So let's talk for a moment about where points would come from, okay, if this was a test or a quiz. So you're going to get 1 point for your number, 1 point for your units, 1 point for significant figures. So that's 3 points so far. And typically I'm going to give you 2 points for your work. So typically a problem is going to be worth 5 points on a test or a quiz. Okay? A point for the correct number that your answer is right. Okay? You've done it on your calculator correctly. A point for the fact that you have your units labeled. A point for the fact that you have rounded correctly so you have the correct number of significant figures. And a couple points for showing your work. Right? So remember, that means that's why I'm asking you to show all your work on your homework assignments, because if you don't show your homework, if I was grading that like a quiz, you'd lose 2 points on every single homework question that you did because you didn't show your work. So you do not have homework this evening, okay? So enjoy your afternoon, and I will talk to you tomorrow.